The second idea that I want to talk about with K values is just how large these values can be. We'll show you mathematically why this is the case when we take a look at the difference between delta G, the free energy, and its relationship to K. But for right now, we need to get used to the idea that K values can be huge. So I'm just going to show you a couple of them here and their corresponding delta G's to give you that sense. So let's just take a look right here. Here is nitrogen as a gas becoming two nitrogen atoms. Fortunately, this is thermodynamically unfavored. As you can see, that's a very large delta G. Because if this reaction did, in fact, happen spontaneously, all the nitrogen in the air around us would be nitrogen atoms. Not such a good thing. Now, what would the K value for this be, for this very, very unlikely reaction? Well, it's a very, very unlikely K value. This says that when I set up the ratio of the stuff on the right to the stuff on the left, that there's essentially nothing on the right. Well, we can't have a value of 0 for K. We have to have something on the right-hand side in this equilibrium, but it is an incredibly small number of nitrogen atoms relative to the nitrogen gas. So get used to the fact that we can have numbers that are as small as 10 to the minus 81 corresponding to delta G values of less than 1,000 kilojoules. Well, here's another example of that. Here we have silver sulfide. This is a solid. It associates in water to make silver ions and sulfide ions. And it turns out the K for this is about 10 to the minus 51. What this says is that this reaction very much doesn't happen. It obviously has a delta G, which is a big positive number. It means that when I put silver sulfide in water, basically nothing happens. It stays as a rock. These ions do not form. Now you might ask, is it also possible to have huge positive numbers for K? And obviously, since these are my negative numbers, if I were to reverse these reactions here, I could have delta G's that were very large positive numbers. So for example, if I do have nitrogen atoms, they will very much drive to the right spontaneously to make nitrogen gas. Delta G for this will be minus 456 kilojoules, which means that K is 10 to the 81. So as we move forward, get used to the fact that we're going to have to start doing a lot of exponent math. You're going to see Kas, Kbs, Kws, Ksps, K dissociations, you name it, and they're going to have values like 10 to the minus 42, 10 to the plus 56, 10 to the minus 14, 10 to the plus 23rd. And the second you start seeing exponents like this everywhere, the first thing you have to think is, boy, I've got to do a lot of exponent math well.